Good morning and welcome. We want to look at the method of weighted residuals. I just can give you only very short introduction to it. But let me ask you, does anybody of you know something about the finite element method? I know there are people taking the course. Very good. Yeah, okay, that's very good. So that's at the math department. We have very highly qualified people for that. And the other method is spectral method. Anybody who has heard of spectral method? So that is even more accurate. So we'll see a little bit about that. Okay, so let's start. So the method of weighted residuals. So, remember what we are discussing is the problem that was 1, that was minus second derivative of our unknown is equal to some given function f of x. And that was an interval between xa and xb. So we want to approximate that. We have seen the finite difference approximation approximates the derivative and also the right-hand side at grid points. And then we replace the derivatives by differences. The finite volume method first takes the integral of that and then looks for approximations to the integral of that over a so-called control volume, like we do in standard fluid mechanics. And now the method of weighted residual follows another approach. What we do here is we approximate the exact solution by a combination of basis functions. So the exact solution, we denote that by u of x of 1 with the boundary condition is approximated by and now we do it the following way, and that is according to my numbering now 19. We start from the very beginning. Denote by UH. H is then referring to the grid spacing, so that it is now an approximation to the U of x. And we do it in the following way, that we take it as a sum of basis functions, say from 1 to n DOF, I call it, degrees, number of degrees of freedom. Then we have here coefficients that we have to determine, and we have here the basis function phi j of x. So that is the idea, and we're following. We have to identify what we are doing here. So the phi j of x are given basis functions which are also called trial functions. And the NDOF is the number of degrees of freedom. If we would use a standard finite element method, that would correspond to the number of nodes. And then we can have different choices of these basis functions, and they determine then which kind of method we get. The most prominent one is the finite element method. I should say that has been used in CFD a lot for incompressible Navier-Stokes equations. And for the finite element method, the phi j of x are local basis functions. And they are usually polynomials. And the example, when you do an element method, you would do that in the first place. That would be the so-called head functions. And they look like that. We have our interval from xa to xb. And then we have also here our grid points, or we call it here nodes, like in the finite difference method, or the faces of the finite volume method. And then we can identify, if we want to, for example, look at the phi j of x. We say we want to take here the xj as an example. Then it will be only locally be different from 0. What we have here is the number 1, here we have the number 0. So at the grid point, or at the node xj, this head function phi j of x has the value 1. And then it is linear, it's a polynomial, it goes down to xj minus 1, where it is 0, and here to xj plus 1 it goes down and to 0. And it is 0 all the way through to xp and to xa. So the red one here, that is the head function. So it is only locally defined to be non-zero, otherwise it's 0. So we can give that formally, but I skipped that. Instead, we want to look at other options. And they could be then spectral methods. And in spectral methods, I take the acronym SM. The phi j of x are global basis functions. That means they are defined in the whole interval. And the ones that are mostly used are Fourier, Chebyshev, or Legendre polynomials. So then we can have a number of them, and it turns out we do not need that many, because this method is extremely accurate. Once we have enough points to resolve the features that we want to do, then we get very accurate results, and when we do then take more, when we increase the number of basis functions, the error drops not linearly, like for an order standard finite difference, finite volume, or finite element method, but it drops more. So the error goes down very much faster. So these methods are extremely accurate, but they are limited to very simple geometries and simple boundary conditions. For example, the Fourier method you can only use for periodic boundary conditions. Chebyshev is more flexible, and also Legendre. But that is the limitation of these spectral methods regarding the complexity of the geometry and boundary conditions. So that is, the one one is missing now, the last one that I want to mention. That is the spectral element method. Acronym SEM. And that is a kind of combination of the finite element method and the spectral method. So in the spectral element method, the basis functions are local basis functions. So we have it, that is common with the finite element method. But these are then not polynomials, but so-called orthogonal polynomials that have nice mathematical properties, and that are in fact the Chebyshev or the Legendre polynomials. So that is, you could say, a combination of the flexibility regarding geometry of the finite element method, also regarding boundary conditions, and the good features regarding accuracy from taking then the local basis functions to be orthogonal polynomials. So in any case, with all these three methods, finite element method, spectral method, and with the spectral element method, what we do is we insert the ansatz that we had in the beginning with the basis functions into the PDE that we want to solve. In our case, it will be the ODE in the beginning. It's an example of what is also done in PDEs. So that means the ansatz, that is the form of the solution, of the numerical solution that we assumed, 19, is inserted into, in that case it was the ODE 1, and then it will yield something that is then related to what we're discussing here, the residual. Because we will usually not get the exact solution with that ansatz, but we will get something that is then called residual. It's the difference between well, it is the error, so to speak, what we get when we insert our numerical approximation UH of x into our problem. And that was this, and on the right hand side we had the f of x, so we take that on the left hand side to see the difference. If that were 0, then we would have the exact solution. So R, the residual, is not 0 unless the numerical solution, or ansatz with the basis function, is equal to the exact solution. So then we have to find these coefficients essentially in front of the basis function, the uj that we called. So that is now done in the following way. We have n d or f, number of degrees of freedom of these coefficients, so we need that number also of conditions to determine them. So we need the number of degrees of freedom as also conditions to determine the n, d or f unknowns, which are the coefficients, the expression 19 with the basis functions. In ansatz 19. So what we can do is we define that number that we need linearly independent and that those are called test functions. And let's call them VI. Let's see where it's 21. VI of x. And we have ND of f of them. So then we try to use those to get conditions for the coefficients in 19. How do we do that? We multiply the residual by these test functions and integrate over the domain. And then we want that to be 0. So that will be our condition. So then we have then the residual, and you can say we weighted these test functions and want that to be 0. So let's see how that works. So we continue here, so we get that. So we require the residual orthogonal to all test functions. And that means the following. So when we have the residual r of x, we multiply it by, say, the test function vi of x, and then we might have a weighting in additional to that we might call w of x, and then we say we integrate over the domain where we want to solve the problem, and then we want that to be 0. So that would be one way to determine these coefficients. And that is the way that is done by the method of weighted residuals. So you see here the name, the residuals are weighted, and we require then that these residuals, in this sense, are orthogonal to all test functions. That has to hold for all I from 1 to the number of degrees of freedom. That means for all test functions vi of x. So that is then also related to the name weight method of weighted residuals. And usually the w of x is 1. Yes?
I'd rather x was 1 than double n.
Yes, it's usually 1. But if you want to have, for example, Chebyshev polynomials, then it is always you get 1 over the square root of 1 minus x squared, something. So it is then orthogonal with that. So where the w of x is equal to 1, that is the usual, or it is some weight function. And that depends on what you want. Now, there are different choices of these test functions, and each choice gives essentially a different method. So, and well, let me just give you that briefly. Test table and the type of method. If we choose the vi of x equal to the delta function, x minus xi, we do this integration and we have the w of x equal to 1. That means that then the integral is equal to the residual at xi. So then we require the residual at the nodes xi to be 0. And that method that we get out of that is called the collocation method. If we choose the test functions in the following way, that we say it is 1 for x in, now we say omega I, that is similar to what we had with the finite volume method, so that would be in an interval, say I, say from grid point, say from grid point I to grid point, or from node I to node I plus 1, for example, it would be 0 else, then we would in fact get the finite volume method. So that is what we did there. If we would use the phi x of, the vi of x would derive the residual with respect to our node xi, then we would get the least squares method. That's the method used by my colleagues Maria Fernandino and Carlos Dorao. They solved many problems with that. vi of x equal to phi I of x. That means we choose the test functions equal to the basis functions. Then we get the Galerkin method. That is the method that is usually used in finite element. If we choose the test function different, say we choose it equal to some psi I of x that is dependent then, but which is not equal to the basis functions, in finite element method, we get something called the Petrov-Galerkin method. So you see we have a couple of choices here, but this is the choice for the finite element method, the usual choice. And if we have certain problems, we would also choose this. So then we can go through this machinery and do that, insert our residual in here. And then in our case, we would have here that would equal 1. Here we would have the second derivative. Then of our basis functions, of the phi j of x, and the sum of all that. And here we would have then, for the Galerkin, the phi I of x. We do the integration. We could use integration by parts, and then we can simplify everything. And if we use then the head functions, we get exactly the same matrix as we got for the finite difference method. But the right-hand side is different, and the scaling is also different, because we have done the integration, so it is not 1 over delta x squared in front of the matrix, but 1 over delta x. On the right-hand side, we have them a little different, because we have to integrate the right-hand side multiplied by the head functions over the interval. And it turns out for my test case that I showed you yesterday that the finite element method happens to be even exact. Okay, just a few remarks on these methods. So if we compare all the methods that we looked at, finite difference, finite volume, and say finite element, spectral method, spectral element method, they are all very useful, but they have certain domains where they are most useful. Say the finite difference method is easy to implement, and it is, has good mathematical background, but it is usually limited to relatively simple geometries in the sense that you must have a mapping from what you're doing to a rectangular domain in 2D or a brick domain in 3D. So that means you cannot do unstructured grids with that. On the other hand, the finite volume method, finite element method, you can do that. They are very flexible regarding geometry, regarding adaptivity. If you want to get more points at some points where things are happening, you can do that very easily. The finite volume method has its strengths that it is doing the conservation laws as they should be done. It is the integral form just as we learned in fluid mechanics. So that is the strength. That is probably why it is mostly used in CFD. The spectral method is extremely accurate, so if you have problems which have simple geometry, simple boundary condition, then use it. It is used a lot for fundamental research like direct numerical simulation of turbulence. And the spectral element is then some bridge between that method, very accurate method, and the more flexible finite element method. So regarding mathematical foundation, the finite difference method is well founded, and so is the finite element method, spectral method, and spectral element method. The finite volume method has a lack here, but it is nevertheless very useful for CFD. Okay, that should be all. Of course, we have to move on. Of course, you could give lectures like we have some of you taking finite element method that you could learn a whole semester, or some people do it for their whole life. So instead we want to move now on and to get now to the finite difference method for the heat equation. So that's now the target of the next chapter. The heat equation is just an example of the parabolic equation, as we saw in the very beginning, with the classification of PDEs. And other examples for that PDE is diffusion equation. And that is also the topic of exercise 4, which is out. And there we look at a problem that I'll mention in a minute. So, the chapter is now 6. The topic is the heat equation. And I think also the diffusion equation. It depends how what you like. We have heat transfer problems. We will focus on the heat equation. We have problems for diffusion of a species in a mixture, or as we have diffusion of velocity in viscous flow, and we would have diffusion. Let's look at a few examples. I call that the physical and mathematical classification. So, classification. And that connects to what we discussed in the beginning when we looked in a general way at PDEs. As examples, I'll take the heat equation. And that is the following. We have the time derivative. I use U here. It will in that case be temperature. Is equal, to the right hand side we have a coefficient alpha, which is the thermal diffusivity, I'll write that in a minute also, times the second derivative of U with respect to x. So that is the heat equation. And that models heat conduction. or we could also say the diffusion of temperature. So it means the U is now temperature in this case, in a 1D isotropic medium. That can be a solid, can be a fluid, liquid or gas at rest. And the alpha, the coefficient appearing in the heat equation, that is the thermal conductivity K that we have from Fourier's law, and divided by the density and the specific heat at constant pressure. This is called the thermal diffusivity. And the dimension is meters squared per second. You will also see that when you look at the equation that it should be like that. So the example that I also want to show you later on is the following. We have a rod, say circular for example, and we insulate that here so that we cannot lose heat around the casing. And we have the initial temperature, x t equal to 0, we take that to 0. So we have it at 0 degrees, so we have outside, for example, today. And then, in my example, I'll heat it, call this here TB, the right-hand side to 1000 degrees Kelvin, and on the left, also it's heated to 1000 degrees Kelvin at t equals 0. And then we want to observe how the heat, in that case the temperature, moves into the rod and how the temperature then changes inside the rod. So that would be an example that we could model by a heat equation. As I said, I'll show you later on this example. Before, let us look at other ways or other equations that we can take under this heading. That would be the 1D diffusion equation. And that looks similar. It is just the meaning that we are studying of the variables and also the coefficients. The coefficient is different. Usually it is some curly d of then d squared u dx squared, and that models diffusion of a concentration U. So that is now concentration, and you measure in some way also the mass fraction, how much mass of that species is in that part regarding to the mass of the mixture. So there is a concentration U in a 1D mixture. And the D is the diffusivity. This coefficient is the diffusivity. And that has also, of course, the same units. And the example that you could imagine is the following. We have, say, again, some pipe, and we have some membrane in the beginning that is a barrier between, say, a water, I call it here the colored water, so we have put some ink in it, for example, and here we have the clean water. Then we remove this diaphragm, then we can see how that would be at t equal to 0, and say at some time later, then t greater than 0 at some point, put maybe here, then we would have both colored and clean water, so the one would penetrate in each other, so they could diffuse, the colored water would diffuse in the clean water, and the clean water in the colored water. So we would have here both colored and clean water. And here we would have still the colored, and here the clean water. And although it affects everything, but where most things are happening is then we can observe that it is not as clear as I indicated here. It is more smeared, but the influence, you can see as the influence gets larger and larger, it spreads. And that is then also a diffusion process. And the one that we are studying for the exercise 4, that is the diffusion of velocity in a viscous flow. So that is the simplified Navier-Stokes equation. And for the case that we are studying, which is related to the startup of coed flow, it turns out that we get the time derivative, now use velocity, is equal to the kinematic viscosity times the second derivative of velocity with respect to y. Because we imagine we have this situation, we have two parallel plates, and the upper plate is moved suddenly. So in the beginning we have here the velocity, if we have u, it is simply 0. But at time equal 0, we suddenly move the upper plate with a velocity v. And in the example that we study, we have everything non-dimensionalized, and that would be 1. And what will happen is, at time equals 0, so now we have the dimensions, that's first the coordinate system, this is x, this is y, so things are homogeneous in x, but happening in y. So if we then look for the velocity in x direction, u, then it would be in the beginning 0, and here it would be 1. And then as we wait a little bit, then it will still be 0 here, but it will feel then this, that it will have to go up there. So and then this will get more and more felt as we proceed in time. So this is, say, t1, this is t2, t3, and you are going to calculate when the velocity in the middle will be 1/2 of what it should be in the steady state. In the steady state, we know that is the basic exact solution of the incompressible Navier-Stokes equations. We will have that is steady state, that is for t infinity. But we are going, so at 1/2 that we are going to calculate, then this velocity will be in steady state 1/2. But we are calculating until it is 1/4. So that we will do in exercise 4. So then we'll study here. So this equation models the diffusion of velocity in a 1D viscous flow. So that models diffusion of, now it is velocity u in a one-dimensional viscous fluid action. And the nu that we have here, that is the dynamic viscosity mu divided by the density, that is the kinematic viscosity. And of course, again, that we know from fluid mechanics, the units, so the dimensions, the units, meters per second. So just a side remark, we can actually also model probably the most solved equation nowadays in the world by diffusion equation. That is the Black-Scholes equation. That's the equation used in mathematical finance to model the development of the price of options. So then we are in business. So regarding so that was a little physical characterization. What is the background of the heat equation and the fusion equation? Now regarding the mathematical characterization, our PDE can be put in the form alpha uxx. Now I'm talking about the heat equation here, therefore this is the thermal diffusivity, plus 0 ux. Our second variable is now time, not y as we had in the beginning, plus 0 times utt. So that is equal, in our case, ut. Lower order terms do not matter. So this is then our A, this is our B, this is our C from the chapter of the mathematical characterization of PDEs. And the discriminant that is determining things is b squared minus 4ac. You see that is 0, b squared is 0 for alpha times c. So that means we get here a 0. And that means that our equation that we are solving, the heat equation, the same is true for the diffusion equation of course, is parabolic. And look at section 2.3 of the lecture where we discussed them. The exact solution can be obtained by separation of variables, or you can find a similarity solution. And you'll see examples in the book. And also, last not least, in exercise 4, you have an example to solve this problem. Exactly. Okay, so then that. Let's see if I can get things started here. We'll take a break. So I want to show you some animation here, and that is related to the problem that I mentioned before for the heat equation. Yeah, so this is now, first I have to tell you, because the x's are not yet out, what these Okay, so first I have to tell you what the x's are. Okay, it's not fully on there. Here we have the x-axis, here we'll have the time axis, and here we have our temperature. So it is 0 all the way through, except at the boundaries we have 1000 degrees. And now the solution will be plotted at each time step. And that means we will now see a solution developing and the solution results for each time, and then we'll get more and more graphs. They will then be plotted in this 3D fashion. So let's see how that works. Oh, very strange that. Yeah, okay, now it's better. So, you see here we have then this solution, and that means we have now a solution that depends on x and t. So, and what we can observe if we look from the side, that the temperature in the interior is increasing. So it's first 0 and then it starts feeling the heat from the boundaries and it is increasing. So, and also from the boundaries the heat is coming more and more into the rod. So that is one way to visualize it. Then it's the function of space and time. That is what we are doing. Another way to do it is to look at just the XU plane. That is, we have here x and u is our temperature. And now we see what is happening at each grid point. So then, shifting the frame, now it should be okay. So now already after just a few time steps, we have seen that the temperature at the grid points close to the boundaries feel what the heat from the boundaries, and temperature there starts to increase. We can go on and we see how the temperature goes up and also how it affects more and more the interior. So the temperature goes up all the way. And the visualization that is done here, that has given the name to the method that we are going to look at after the break, method of lines. So we do a discretization in space, and then we keep the time continuous, and we solve then at each point, we solve then this ODE that we get in time. And then we can see the development of the solution at each grid point in time. Okay, so then we take 15 minutes break.